So in the last discussion, we had covered the first part of this, that is SIP and uh, SIR, basic things, and we have discussed mainly steric inhibition of resonance. Okay, so we have discussed the problems of benzoic acids, and which is also called ortho effect. Now let's discuss steric inhibition of protonation, SIP. And this both steric inhibition of resonance and steric inhibition of protonation, both are useful in describing basicity of amine. So basically the topic is basicity of amine, aromatic amine, that is aniline. This is our aniline. Now before going into that, if I ask you a question, compare basicity of this aniline molecule with simple aniline. Second one is aniline with electron donating group. This type of writing means you can consider it is in ortho position or meta position or para position. And the third structure will be aniline with electron withdrawing group in a generalized discussion, NH2. So 1, 2, and 3. If I ask you that what will be the basicity order, I think you have thought already, or you have answered already in your mind. So actually the answer is electron donating group will be most basic, because electron donating group will generate more negative charge on this nitrogen, that will repel the lone pair, and lone pair will be more available to attack. So that will be acting as Lewis base. Basically all these three amines will be acting as Lewis base, and electron donating group will pushing electron toward nitrogen, and that negative charge density will be there much. That's why that will repel the lone pair to attack more favorably. Okay, so first will be electron donating group, that means 3, then normal, then 2, then 1. Okay, now the problem arises when in aniline, if I add different groups. For example, it is our cute aniline, NH2. Now there is one group. Now what happen if I want to compare stability of different aniline molecules? Then we have to draw its conjugate acid, because it is base. So stability will be decided by basicity will be decided by stability of conjugate acid. So the conjugate acid will be when it will abstract proton, the resultant molecule will be our conjugate acid. So our conjugate acid will be NH3 plus, and this is the group. Now what will happen? Initially there were 2 hydrogen, and now here is 3 hydrogen. If this G group is bulky, then hmm, if this G group is bulky, then what will happen? This extra hydrogen will generate an steric hindrance with that G group. Okay, and more bulky the G group is, it will hinder the upcoming proton. So for example, in another case, the G group is very much bulky. Then if the protonation occurs NH3, then it will be very much stable, because initially there were 2 hydrogen and now there is third hydrogen. So there will be too much steric hindrance. So this G group will prohibit this molecule to get protonated. So this protonation will be hampered. If G group is bulky, then it will not allow that this aniline molecule to abstract proton, because abstracting proton will generate a lot of steric hindrance. So basically, steric hindrance of G group is prohibiting the protonation. So it is steric inhibition of protonation. So steric hindrance is basically prohibiting a protonation process. Now, if this G group is not bulky, this is a small group, then there will be no steric inhibition of protonation. Then very finely, the hydrogen can add up here and the protonation can occur. So how will we decide that which groups are uh, you know more bulky or less bulky? If the G group is hydrogen, deuterium, tritium, fluorine, OH, note them down, okay? NH2 and CN. So with these groups, there will be no steric inhibition of protonation. And this similar kind of thing also applies for this ortho effect. If in place of CH3, these groups are there, then also there will be no ortho effect or steric inhibition of resonance. Okay, so now tell me one thing. If there is a more steric inhibition of protonation, let me write. Let's see, if G group is more bulky, G group has bulkiness more, then steric inhibition will be more. That means steric inhibition of protonation will be more. Then this molecule will not like to abstract proton. Then the basicity of this molecule will be lower. So basicity will be lower. So more the SIP, more the bulky the group is, lesser the basicity. So what we can conclude from here is steric inhibition of protonation is basically inversely proportional to basicity of aniline. So basicity of aniline is inversely proportional to steric inhibition of protonation. I hope this is very much clear to you. Now let's go to another fold of this concept. Now, till now I have discussed the steric inhibition of protonation. If there is any one group rather than hydrogen, for example NHR, so it is not aniline, it is basically substituted aniline, N substituted aniline. Or there is, for example, NR2, this is basically aniline, this is basically 3-degree amine, 3-degree aromatic amine, okay? NN disubstituted aniline. For this molecule, steric inhibition of protonation, this thing occur, but this thing is not so prominent here. Another thing that becomes prominent is steric inhibition of resonance. This become very much prominent. How steric inhibition of resonance is applied here? We have learned till now the ortho effect in benzoic acid where steric inhibition of resonance can occur. Now let's see what will happen if I want to compare acidity, if I want to compare basicity of this molecule, for example. Now let's take two examples. In one example, there is NH2, uh, sorry, NHRG. Another one is NHR, for example, um, small, S for a small group. For example, a small group, G for bulky group. Okay, or you can write large. So small group, large group. What will happen if I want to compare the basicity of these two molecules? Let's see what will happen. Here, because of this large group, generally another thing, if this is aniline NH2, and if I compare it with, for example, this amine, which will be more basic, this will be more basic. Why? Because nitrogen lone pair is basically undergoing resonance with this benzene ring. That's why it is less available to donate, right? That's why aromatic amines are generally less basic. Similar things, if there is very small group, then what will happen? This lone pair will undergo simply resonance. Okay, now if I am able to hinder it in such a way that I am able to stop the resonance of nitrogen with this ring, then the basicity of nitrogen will be very much higher. So in somehow, if I am able to restrict the resonating structure, if I able to break the resonating structure of nitrogen with that benzene ring, then the nitrogen will be very much basic. Now, if there is a large group, then what will happen? Similar kind of concept in one plane. For example, if nitrogen want to show resonance with that benzene ring, what will happen? Lone pair will have to situate in this way. These are another two group. Lone pair and the pi bond should be parallel to each other. Okay. Only in this case, uh, only in this case, resonance will occur of nitrogen lone pair can undergo resonance with this benzene ring. Now consider if there is one very bulky group in ortho position. For example, this is a bulky group, large group in ortho position. Now this group will undergo very much steric hindrance with this. So with this steric hindrance, what will happen? To omit this steric hindrance, this single bond will undergo a rotation. With this rotation, what will happen? Now our ring is like this. Now nitrogen is large group. Now two groups are, for example, methyl or hydrogen. Two groups are now perpendicular. If this is perpendicular, there is no steric hindrance. Okay, because there is bulky group, and one group is like this way. This to nitrogen. If with this bulky group, this is in perpendicular position, then the steric hindrance is in this position. Okay, so this will be steric hindrance will be reduced. In this case, nitrogens, for example, CH3 and CH3 or H. So steric hindrance of groups associated with nitrogen is like this way. But if it undergo this bond rotation, what will happen? This both group will be like this perpendicular, then the steric hindrance actually reduces. Okay, so that's why the steric hindrance will be reduced when the bond rotation occurs. For this, what will happen? This lone pair is now out of this plane, out of this benzene ring plane. Uh, I mean, it is not parallel to this pi electron cloud. Now, this lone pair will not able to undergo resonance because it is not parallel. So if it undergoes resonance, this gives stability. But if it want to give stability by undergoing resonance, then the steric hindrance will be very, very much. So that will unstabilize the system. So there is the competition between the resonance stability and the steric hindrance. Because this is NHR, that means one alkyl group is there. Huh? As one alkyl group is there. That's why the steric hindrance is very, very much prominent. If there is two hydrogen, then the steric hindrance will not that much prominent. Okay, that's why if there is only two hydrogen, NH2, that system will not rotate this single bond. It will rotate the single bond only if there is at least one group, one R group or one methyl group or both the methyl group or both the R group. Understood? So in this large group, actually this bond will rotate, and when the bond will rotate, this lone pair will not undergo resonance with the benzene ring. Then my friend, then the lone pair is very much available for donation. So this is very much stable and very much basic, rather I would say very much basic. So with these two compound, first one is much more basic because here also steric inhibition of resonance occurs, you know, because this bulkiness of this L group is disrupting the resonance of nitrogen lone pair and benzene ring. So it is steric inhibition of resonance. So steric inhibition of resonance is acting here for bulky L group, but there is no SIR for this small group. Now the group having more SIR is we are getting more basic. So here we can conclude basicity of amine is proportional to steric inhibition of resonance. Now we have received two critical information. Let me add another page. Mm, okay, so we are getting two different information. If it is normally primary amine NH2 and there are different groups, then we will have the steric inhibition of protonation and basicity proportional to 1 by steric inhibition of protonation for 1 degree aromatic amine. This is 1 degree amine and aromatic amine. But if here is NH2, sorry, NHR or NR2, then there is different group. Then we will be having steric inhibition of resonance. Then here basicity is proportional to steric inhibition of resonance, right? So I think it is very much clear to you. Now, if I give one question for this practice, tell me, let's write the question. NH2, NH2CH3, NHR, NHR, CH3, and fourth one is NR2, CH3. And CH3 is a bulky group, right? In that list of a small group, I have not written CH3. That means you have to consider CH3 as a bulky group. Now my question is, arrange this 1, 2, 3, 4 in accordance with their basicity. If you can make it correct, if you make it correct, then your concept is clear. So try. Okay. Now, least basic will be NH2 CH3. It will be least basic. Why? Because in this molecule, we know steric inhibition of protonation will be applied. But for these two molecules, steric inhibition of resonance will apply. And more the steric inhibition of protonation, we know steric inhibition of protonation decrease basicity, right? They're inversely proportional. So basicity will be least for this. Now for these two SIR is getting applied. And for SIR, we know more the SIR, more the basicity. If NHR is there versus NR2, then NR2 will show more steric inhibition. So basicity will be maximum for among these two, 3 and 4. We will have first NHR, then methyl, then NR2, then methyl. Now the question comes that aniline, for simple aniline, what will be the case? Uh, uh, hmm. For simple aniline, now we know with normal aniline, what happens? If aniline G group is hydrogen, that means it is small group. For more, for bulky group, you know, for bulky group, for aniline case, for substituted aniline, for more bulky group, we will be having steric inhibition of protonation. And more the steric inhibition of protonation, lesser will be the basicity, right? That's why the NH2 and methyl, it is the least basic. Now, for simple aniline, if there are two different groups, there are NHR and NR2, what happens? Steric inhibition of resonance. This group is basically hindering the resonance. That's why these groups are not able to undergoing resonance with this ring. That's why it is very much available for resonance, right? So our aniline will be in this position. This position. It will be more basic than the orthomethyl, because the methyl will be hindering protonation, and it will be lesser basic than this, because in both the cases the lone pair cannot undergo resonance with this benzene ring. Here also lone pair cannot undergo resonance with that benzene ring, but here also, yes, it can undergo resonance with the benzene ring, but the protonation will lead the steric hindrance. But for aniline, there will be no steric hindrance after protonation, right? So this will be the order. So I hope you have understood the basic thing of steric inhibition of resonance and steric inhibition of protonation. But there is a special concept of proton sponge. As I am discussing the aniline kind of things, there's a concept of proton sponge. I will be discussing in the next session. Okay, so proton sponge is a very special kind of problem where the basicity is exceptionally high. proton sponge. That means it's a kind of a sponge that is abstracting proton. As a sponge attract water, if you put a sponge in water, in the similar way, how there is affinity, the water with that sponge. That means proton affinity, water affinity for a sponge is too high, and the molecules we will be calling proton sponge. Those molecules will have that much of proton affinity towards the base. So that means those base are very, very strong. So we will be discussing that in the next session. Till then, bye bye.